16 million years ago, a cataclysmic supervolcano eruption in the American West created the lithium foundation for 21st century military systems. Modern defense platforms require immense volumes of lithium to power everything from dismounted infantry communications to the flight control surfaces of stealth aircraft. This diagram of the defense supply chain reveals a critical vulnerability. While raw materials are extracted from Australian hard rock mines or South American brine ponds, they are currently shipped to China for midstream refining before they can be used. This reliance creates a geographic bottleneck that threatens the long-term operational capability of the nation's energy and defense infrastructure. The solution lies buried along the Nevada-Oregon border within the McDermitt Caldera. This basin holds tens of millions of tons of lithium, making it the largest known resource of the metal on Earth. For decades, the United States operated only a single producing lithium mine, relying on the slow solar evaporation of subterranean brines. Converting these volcanic sediments into battery-grade chemicals requires moving past traditional mining. The ore here demands a total commitment to high-pressure chemical engineering. To bypass foreign processing hubs, the United States must master the microscopic chemistry required to pull elemental lithium directly from ancient, heavily bonded clay. This deposit began 16 million years ago when a supervolcano erupted and emptied its magma chamber, causing the overlying crust to collapse into a vast crater called a caldera. Looking at the center panel of this geological life cycle, we see how a closed basin lake formed within that depression. Because the water had no outlet to external rivers, the highly reactive volcanic ash that rained into the basin was permanently trapped. Moving to the present-day cross-section on the right, we see the result of millions of years of chemical alteration. Trace lithium atoms from the ash were incorporated into the crystalline lattice of newly forming smectite and illite clays, specific types of microscopic layered minerals. This geologic trap created an enormous resource, but it left the lithium physically locked at an atomic level inside a microscopic mineral lattice. Because the lithium is trapped inside the clay structure, you cannot simply crush the rock and sift it out. You must chemically dismantle the host mineral itself. This chart comparing sulfuric acid consumption highlights the extreme resource intensity of this process. Extracting just 1 kilogram of lithium from sedimentary clay requires 23 kilograms of highly corrosive sulfuric acid. As this fluid dynamics comparison shows, mixing acid with these clays creates a thixotropic gel. A thixotropic material is thick and gel-like when stationary, but flows under mechanical force, a property that can snap the steel blades of standard industrial mixers. When concentrated acid attacks the clay matrix, the reaction releases an immediate spike of thermal energy, creating boiling, corrosive mud that threatens standard industrial equipment. Protecting the equipment requires constructing massive, custom-engineered vessels. An outer shell of carbon steel is lined with an impermeable rubber membrane, which is then shielded by multiple interlocking courses of acid-resistant ceramic brick. Regulating the heat inside these tanks is critical. If the temperature spikes past specific limits, the heat will breach the protective brick and melt the underlying rubber membrane, leading to the rapid destruction of the tank. Once the mineral is dissolved, engineers arrive at the final bottleneck, using massive, high-pressure filter presses to physically squeeze the liquid lithium solution out from the microscopic pores of the clay. A commercial lithium clay operation is an integrated chemical refinery, where the extraction of the mineral is inseparable from the management of corrosive fluids. Sustaining this process requires thousands of tons of sulfuric acid every day. Because trucking that volume of hazardous liquid is logistically impossible, these sites must build massive on-site plants to manufacture their own acid from raw elemental sulfur. Burning thousands of tons of sulfur produces high-pressure steam, which is used to spin turbines that power the entire refinery in island mode. This means the facility operates completely independent of the regional electrical grid. By co-generating its own power and manufacturing its own primary reagent, the project is insulated from external acid market price shocks and grid instability. By combining the mine and the refinery on a single site, the final product leaving the desert is a highly refined chemical ready for direct insertion into domestic gigafactories. This process removes adversarial midstream leverage. By eliminating the transoceanic transit of raw concentrates, the supply chain for defense platforms remains within domestic borders. The integration of ancient geology and modern engineering allows the United States to bypass foreign refining hubs, keeping the entire life cycle of defense energy within a single sovereign loop.